Hi, my name is Summer, and this is my lab report on the magnetic field of a bar magnet. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare our measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the PHYS law. The PHYS law relates the magnetic field produced by an object at an observation point to the current going through the object and the distance between the source of the field and the observation point. The value of the constant mu naught over 4 pi is 1 times 10 to the negative 7 newtons per amp squared. The magnetic dipole moment is a vector that points from the south pole to the north pole, shown by this equation. It describes the magnetic strength and orientation of the magnet. The magnetic field comes out of the north pole and goes into the south pole. The direction of the B field is determined by the direction of the current in the loop. The on-axis magnetic field is the magnetic field that passes through the center of the loop perpendicular to its plane. The off-axis magnetic field is the magnetic field that is not on the axis of symmetry of the magnet. The perpendicular axis magnetic field is perpendicular to the axis of the bar magnet. Each equation is shown here. The distance dependence equation can be expressed by this equation shown here, where K is a combination of constants and parameters that don't change during the experiment. We expect the magnitude of the magnetic field to decrease with distance, so n should be a negative number. To determine the experimental value of n, we use curve-fitting software, where we take the logarithm of both sides of the original equation. The main results of this lab was that n was found to be negative 2.442, which is a negative number. The magnetic dipole moment was calculated to be 5.385 amps times meters squared. The magnitude of the experimental off-axis magnetic field was 9.521 times 10 to the negative 5 teslas, and the magnitude of the computational off-axis magnetic field was 7.349 times 10 to the negative 5 teslas. First, we downloaded the magnetometer app. Next, we compensated for magnetic north due to the presence of the Earth's magnetic field. We also found the magnetometer chip in our smartphones. Then we measured the distance between the magnet and magnetometer, where the magnetometer is on axis to the dipole axis of the magnet. Finally, we measured the off-axis magnetic field by measuring the off-axis distance between the magnet and magnetometer. The system in this experiment is the magnetometer, and the surroundings is the bar magnet. And here's a picture for one of the parts of the lab. Here is the data collected from each part of the experiment and the graph that was created showing natural log of bx versus natural log of r. This graph shows a line with a negative slope, which means that the magnitude of the magnetic field does decrease with distance. Some observations we made was that when the magnetometer was far away from the magnet, it did measure a near zero magnetic field in the x direction, and as the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased. For example, at 20 microteslas, distance was 0.3 meters, while at 70 microteslas, distance was 0.185 meters. Using the linear equation from the graph, the slope is n, which is negative 2.4442, and the y-intercept is the natural log of k. This means that k is equal to 1.077 times 10 to the negative 6. We can set the distance dependence equation equal to the on-axis magnetic field and plug in these values of k and an approximate r to equal 1 to solve for the magnitude of the magnetic moment shown here. For the computational model, here is the function created to calculate the magnetic field using the general formula for the magnetic field of a magnetic dipole. Here is the code for drawing and scaling multiple arrows on axis and perpendicular to the axis to visualize that magnetic field. Then we also incorporated the code for calculating and drawing the off-axis magnetic field arrow. Here are the results from the computational model showing the arrows for on-axis, perpendicular axis, and 45 degrees off-axis. We can use the vector magnetic field of the off-axis arrow to find the magnitude, which is calculated to be 7.349 times 10 to the negative 5 teslas. As we had expected, as the distance between the magnetometer and the magnet decreases, the magnitude of the magnetic field increases. The experimental and computational magnetic field magnitudes slightly differ, which could be due to possible sources of error. Some of these sources of errors were other sources of magnetic fields nearby, which could distort the measurements, inconsistent placement of the phone by slightly moving the phone during measurements or not keeping it flat. There may have also been measurement errors with magnetometer app and rounding errors in calculations, leading to inconsistencies in data collection. To answer the what-if questions, if we hadn't oriented our experiment to compensate for a magnetic north, and instead we had laid the meter stick at an intermediate angle, our measurements would be different and might even be lower than expected. Since Earth's magnetic field is a vector, measuring along a misaligned direction would capture only a portion of the total field strength, reducing the accuracy of our results. On the other hand, if we were able to stick two identical magnets together end to end, effectively doubling the dipole moment, the measured magnetic field would be stronger, especially close to the magnets. The field would still decrease with distance, but at any given point along the axis, the strength would be greater than that of a single magnet.